So let's start by going over one of the exam problems, actually. What we're going to focus on today is physics, motion, applications. And one of the exam problems was about that. It was this problem right here, number 13 on the exam. The height y of a rock dropped from the top of a tall building is given by a function of t. F of t equals negative 4.9 t squared plus 100, where t is in seconds. Want to find the average velocity from time 0 to time 2, and find the instantaneous velocity at time 1 as a limit calculation, calculating the derivative. So let's go ahead and write this function down and show you how to do this problem. Then we're going to use Mathematica to help us understand what's going on and be able to apply more complicated models and calculus to more complicated models to help us understand what's going on. So the function here is f of t equals negative 4.9 t squared plus 100. I called it y on the exam. That's fine. I could have called it s like we did last week when we talked about position. I could call it h for height. So y is the height in meters. In meters. And t is time elapsed in seconds. And the goal is to be able to compute both average and instantaneous rates of change, give their units. And I could have also asked you to interpret their meaning. Okay, so let's go ahead and do that. So the average rate of change from t equals 0 to t equals 2, you could write symbolically as delta y over delta t, change in y, change in height divided by change in time. With function notation, that's f of 2 minus f of 0 divided by 2 minus 0. Before we calculate this, let's think about it. Let's start thinking about the geometric meaning. Let me go ahead and graph this function. Y is a function of time. It's quadratic. Its graph is a parabola. If you plug in t equals 0, you get the y-intercept. You get it to be 100. So if that's 100 right there, that point is on the graph. And, well, there's no linear term in here. The initial velocity is 0, is what that means. That means you're dropping the rock from rest. Initially, its initial speed and its initial velocity, for that matter, are 0. And that means the graph has a horizontal tangent right away, though it does start curving downward and looks like half of a parabola, about like that. A purely algebra problem is to figure out when it hits the ground. If y equals 0 is the ground, when does it hit the ground? When does it hit the ground? That was not an exam question, but it would be a question I could have asked on the exam and you should have been able to answer. What do I do? Solve for t. Set y equal to what? 0 and solve for t. So negative 4.9 t squared plus 100 will equal 0. So 4.9 t squared will be 100 if I add 4.9 t squared to both sides. Divide both sides by 4.9. T squared is 100 over 4.9. So in exact form, and since the spot where it hits the ground is at a positive time, I can take just the positive square root of 100 over 4.9 which if I like, I can write as a square root of 1,000 over 49. Those are the same thing. Doesn't really matter. 100 divided by 4.9 is about 20.408. Take the square root of that, you can raise it to the 1/2 power, about 4.52 seconds is your estimate for when it's going to hit the ground. Is this a perfect estimate? No. Why not? What does this model ignore in physics speak? What air resistance? It's ignoring air resistance. Turns out to be pretty accurate if it was falling in a vacuum, but when is something falling in a vacuum? Like pretty much never. So in the absence of air resistance, this would be pretty accurate, but there is air resistance. Now, of course, air resistance is a more prominent force, so to speak, when the object is like a feather or something compared to a rock, but it still does have effect on a rock. So this is just an estimate. But that is a purely algebra problem. Rates of change are more like calculus, although if they don't have limit signs in there, if we're not taking a limit, then technically it's still not quite a calculus problem. And what should I expect for this answer? Do you think it's going to be positive or negative or zero? It's going to be negative. This is about 4.52 here. 2 is right around there. This is going to be a slope of a secant line connecting 2 points on the purple graph, a straight line connecting them. The slope of that line is negative. We should get a negative answer here. So plug in 2, we get negative 4.9 times 2 squared plus 100. Plug in 0, we get, well, when you plug in t equals 0, you get 100. All divided by 2. The 100s cancel. Negative 4.9 times 2 squared. 2 squared is 4. That's going to be negative 19.6 divided by 2. Hey, how about that? Negative 9.8. It's just a coincidence that it came out to be the same thing as g here, the acceleration due to gravity. That's not always going to happen. In fact, if I did it from time 0 to time 3, it would not be negative 9.8. The units of the acceleration are meters per second squared, but this is not an acceleration, it's a velocity. So its units are meters per second. But it is negative. That's indicating that the rock is going downward. Y is decreasing. On average, at least, and well, actually decreasing overall. Does that make sense? Yeah, let's go ahead and do it from t equals 0 to t equals 3, just to show you it's different, even though that wasn't asked for. Average rate of change from t equals 0 to t equals 3. That'll be f of 3 minus f of 0 divided by 3 minus 0. F of 3 is going to be negative 4.9 times 3 squared plus 100. We're still going to subtract 100, but now we're going to divide by 3. Actually, a little trick here to say, avoid your calculator even, is to realize this is going to give you negative 4.9 times 3 squared over 3, and one factor of 3 will cancel. I could have canceled one factor of 2 on the other one. So this is ultimately negative 4.9 times 3, which is negative 14, excuse me. Yeah, negative 14.7 meters per second is the average rate of change, the average velocity. These rates of change are velocities. Over the interval from 0 to 3, it's more negative than the other one was. The graph of the secant line is steeper. When I go up to t equals 3 and connect the dots, that's a steeper secant line. It's got a slope that is further away from 0. And since it's a negative slope, it's got to be a negative number further away from 0. Okay, so the fact that these average velocities in this context are negative tells you that on average, the rock is falling downwards. Y is decreasing. Now, again, it's actually decreasing the entire time. But if you didn't know that, all these things would tell you is on average, it's decreasing. Negative slopes correspond to decreasing the functions. And if you're talking average slopes, average rates of change, then they're functions that on average are going down. Those they still could go up in theory. But now we do the calculus. We also want to find the instantaneous rate of change. Instantaneous rate of change. If I could spell, instantaneous rate of change at, emphasis on the word at, t equals 1. This is technically not a ratio. It's a limit of ratios. We use the derivative notation for this. This is going to be f prime of 1. Also, there's that other notation for derivatives, and this comes up in the 3 blue 1 brown video, the second one that I want you to watch, is to write this in this case as dy dt evaluated at t equals 1. The vertical line and when t equals 1 just means plug in t equals 1 after you take the derivative. Or in this case, if we're going to use the limit definition, plug in 1 actually right away. It's a limit as delta t or h, whatever letter you want to use. I'll use delta t here because I've been using it so far. As delta t goes to 0 of delta y over delta t. It's not a ratio in and of itself. It's a limit of ratios. That makes you think it is a ratio, dy dt. It looks like it's dy divided by dt. That's not literally what's happening, though, as I've emphasized, we can pretend it's what's happening. And that's a useful thing to do sometimes. I call it a convenient fiction. Calculus is actually full of convenient fictions about limits where you're pretending something is happening, but it's not literally happening. We're pretending this is a ratio of a distance divided by time, or change in position divided by time elapsed. But to do it, you just need to calculate the limit. Just like you did on the exam, plug in 1 and add delta t. And again, if you did that with an h on the exam, which probably most of you did, that's fine. I'm using a delta t here to emphasize it's a change in time. Delta t just represents one variable, not two variables. It's not delta times t. It's delta t. Change in t. There's a little bit of a pain here because the function has two terms in it. Remember, it's negative 4.9 t squared plus 100. So that makes this expansion a little bit of an extra pain because you have the extra, well, 4.9 in there, and you also have the extra plus 100. Replace t with 1 plus delta t. That expression right there is f of 1 plus delta t. I went to the formula at the top, which was negative 4.9 t squared plus 100, and I replaced the t with 1 plus delta t. On the exam, you should have replaced it with 1 plus h. F of 1 is still, well, it's plug in t equals 1, you get negative 4.9 times 1 squared plus 100. The 100s are still going to cancel here. You've got to distribute that minus sign through the parentheses here. You're really subtracting 100 ultimately. And actually, all of the terms that don't involve delta t will cancel. If I expand this binomial, FOIL it effectively, 1 plus delta t times 1 plus delta t, and then multiply by negative 4.9, I'll get negative 4.9 minus 2 times negative 4.9 times, well, plus 2 times negative 4.9 times delta t, which is really minus 9.8 delta t. And then a minus 4.9 delta t squared. I'm just about out of room on this piece of paper here. I'm also really adding 4.9 right here. See that? Those two negative signs cancel. That's good because that allows me to cancel anything that doesn't involve a delta t. That's what I was hoping would happen. Now all that's left on the top are these two terms, and they both have a factor of delta t that can now be factored out and divided out with the delta t on the bottom. That's what we're hoping would happen. If it doesn't happen for this kind of problem, you know there's a mistake somewhere. Because if it doesn't happen, you won't be able to evaluate the limit. Factoring the delta t out, I get this. Now divide the delta t's out there. And what's left is a continuous function of delta t at delta t equals 0. Go ahead and evaluate this limit by plugging in delta t equals 0. You'll get negative 9.8 minus 0 is negative 9.8. Hey, what a coincidence. The instantaneous rate of change at time 1 is the same as the average rate of change from time 0 to time 2. Is that a coincidence? Well, with quadratics, it turns out the instantaneous rate of change halfway through an interval is the same as the average rate of change from the first point of the interval to the last point. That happens with quadratics, like this function here. This is a t squared function. It's a quadratic. Its graph is a parabola. So yes and no, it's a coincidence. And it seems like a coincidence that happens, but no, it's not really a coincidence because of the fact that this is a quadratic function and 1 is halfway between 0 and 2. That's why it happened. We just confirmed that the slope of the tangent line to the graph at t equals 1, the tangent line to the graph there also has a slope of negative 9.8. It is negative. The instantaneous rate of change of the height with respect to time at time 1 is negative 9.8 meters per second. And yeah, it's meters per second, not meters per second squared. This is not an acceleration. It is a velocity. The average rate of change here, or the instantaneous rate of change, is a velocity for this kind of example. How can this be used? Well, for one thing, it does tell you what the velocity is at that moment in time, if you needed to know it for some reason. For another thing, it can help you approximate function values at other spots, which might not seem like such a big deal. It's like, well, why wouldn't you just use the formula for the function itself? And that is a good question to ask. But it turns out what I'm about to show you is still important, conceptually speaking, for other reasons. We just found that ds dt, or dy dt, evaluated at t equals 1 is equal to negative 9.8 meters per second. That is the velocity at time 1. You could write that as v of 1 if you like. We can then use this information to estimate the height at, say, time 1.1, for example. The height at time 1 is y of 1, f of 1, which was negative 4.9 times 1 squared plus 100, which is going to be 95.1 meters. That's a height. What is y at 1.1? What is f of 1.1? Well, obviously, I could just plug it into the formula for f. That would be the best thing to do, technically speaking. Gives you the best answer. However, again, this concept of using the derivative as an approximate rate of change over some tiny interval is still useful for other contexts And so it's still worth emphasizing. I could say this is approximately f of 1 plus the change in y, the height at time 1 plus how much y changes over the small time interval. Well, that I can say that's an equals, and this is approximately f of 1 plus the derivative dy dt evaluated at 1 times the change in time, which is 0.1. This is going to be a 0.1 right there. The derivative we found to be negative 9.8. So what I need to do is take 95.1 minus 9.8 times 0.1. This is 0.98. And therefore your approximation is 94.12 meters. That would be your approximation using the derivative as a rate of change for the height at time 1.1. Is it exactly right? No, it's not. It's a tangent line approximation. If I zoomed in on the previous graph, near time 1, make it bigger here. Here's time 1. This point has coordinates 1, 95.1. Time is 1, the height is 95.1. We're trying to estimate the second coordinate of this point. 1, leave it blank for the moment. We have just used the tangent line to do that approximation. Tangent line looks about like this. Because the graph is concave down, the tangent line is going to be above the graph. And that means the estimate that we get here, which is going to be on the graph of the tangent line, will be above the actual value. The actual height is going to be a little lower than this. The second coordinate of this point is 95.1. This quantity, 0.98, is really the height of this little triangle that I'm drawing here, this little right triangle. Though we need a negative sign because the function is going downward, not upward. As a change, you'd want to think of that as negative 0.98. To this point right here is going to have coordinates 1.1, 94.12. And I see I made a typo here. This should have been a 1.1 in here. What's the actual height at time 1? 1.1. Plug in 1.1 into the function, negative 4.9 times 1.1 squared plus 100. This quantity, when I compute it, is going to be a little lower than 94.12. How much? I don't know until I actually do it. Negative 4.9 times 1.1 squared plus 100, 49.071 or 94.071 is the actual height at time 1.1. The 94.12 is our approximation to the height at time 1.1. Am I being clear about the fact that, yes, doing what I just did on the calculator is the way to get the more precise answer, more accurate answer, you might say. So again, why am I bothering with the derivative to approximate it? Because it's a useful conceptual tool to understand that this can be done. And it's useful in practice sometimes. Sometimes all you have is rate data. You don't have a formula. I can't emphasize this enough. Sometimes you don't have a formula for a function. All you've got is data. And the data could be height data, for example, or it could be velocity data. And based on that discrete information, you might have to do a linear approximation because there's no formula. That's one reason to do it. And again, it's also a good conceptual thing because it will help us in our modeling especially with something called differential equations, to use derivatives in modeling to do fancier things, you might say. You do want to understand this concept. This is the heart of differential calculus right here, is understanding this concept, what I've just done. I could also try approximating the position at time 1.2. What's the height at time 1.2? That's f of 1.2, f of 1 plus delta y. I could do a linear approximation there. I could do f of 1 plus the derivative, dy dt, evaluated at t equals 1 times delta t again. But now delta t is going to be 0.2, not 0.1. This is going to be 95.1 minus 9.8 times 0.2. This is now a minus 1.96 instead of minus 0.98 like it was with this one. And that's going to give us an answer of, if you do it, 93.14 meters is our approximation for the height at time 1.2. What's the exact height? Use the function itself. The exact height, or the better approximation, since we're ignoring air resistance, is negative 4.9 times 1.2 squared plus 100. This picture still applies. The purple graph is still concave down. That means the red tangent line is still above it, giving us values that are too high. The actual height at time 1.2 is going to be smaller than this, lower. Negative 4.9 times 1.2 squared. Oops. Negative 4.9 times 1.2 squared plus 100 is the more accurate answer, 92.944. That's the answer we got using the derivative. This is the more accurate answer using the function itself. The distance between these two numbers is bigger than the distance between these two numbers. Compare. These two numbers are about 0.05 units apart, right? 94.12 minus 94.07 is 0.05. These two numbers are further apart, more like 0.2 almost. That shouldn't be surprising if you think about the graph. We're going further away. The purple graph here, because it's concave down, is going further away from the red line as t keeps increasing. So you shouldn't expect the approximation to be better. You should expect it to be worse. But the conceptual point still stands. You can still use the derivative as a rate of change to approximate the function. And that is an important thing. It's the important thing on all of differential calculus. Again, sometimes because you only have data and not a formula, and sometimes because it's just useful to understand this in terms of the modeling with, like I said, differential equations. Can I clarify anything? This is really key stuff. All right, I'm about to show you Mathematica that will expand on this stuff. On the homework due Friday, there will be one problem where I have you make a graph in Mathematica. So let me show you the basics of making graphs. First of all, here we go, Calculus 1, Class 14. I will share this Mathematica notebook with you. I'd also like to show you some of the power of Mathematica here by being a little extra fancy. Let me first show you the kind of plot you should be able to make for Friday's assignment. The basic plotting command is called plot with a capital P. And then you have square brackets. What goes inside the square brackets? What's the input of the plot function? Well, the function you want to graph is one of the inputs, negative 4.9 t squared plus 100. That's the function we want to graph. Then you put a comma, and you make what's called a list in Mathematica, indicated by the curly braces that I just drew there, that I just typed. And it's good to type them both right away, because one common error people make in Mathematica is they either forget commas and where they belong, or they forget to end their square brackets or their curly braces. Inside there, you put the variable t, comma, and then an interval, a t min and a t max separated by a comma. How about, 0 to 5? That would be a time interval. This will make a plot if you enter it. How do you enter it? Make sure your cursor is on this line somewhere. It doesn't matter where. Hit Shift Enter. That's what I just did. I hit Shift Enter. Shift first, then Enter. There you have your graph. Okay? That's the most basic thing to be able to do with graphing, is making a plot of a function. Question? You don't, because Mathematica will pick a Y range for you. If you want to pick the Y range, good question, you can, but it's an extra thing to do in here. You would think maybe you do something like this. But Mathematica doesn't know you want to call the dependent variable Y. So instead, you do something different. You type plot range with a capital P and a capital R. And then arrow, you make an arrow by doing a minus sign and a greater than sign. And then you make a list with curly braces with the Y min and the Y max inside separated by commas. And watch, this arrow will magically change into an arrow. Woo! It just magically morphed into an arrow there. There we have the graph on a slightly different Y range. I could change it. I could change this 100 to 1,000. Now it made the Y range 0 to 1,000. Okay. So this is pretty basic. And it's at this level of basicness that I'm going to have you do this first homework assignment where you use Mathematica a little bit. We'll continue to build up your skills with Mathematica. I'm going to do more now in class to show you why Mathematica is so useful. But what I'm about to do is fancier, but I think the fanciness is worthwhile. I'm going to define a function that's going to represent my height as a function of time. But I'm going to be kind of fancy for good reason that I'll explain as we go here. I'm going to have this function have, well, it's going to really be a family of functions. I'm going to use this writing assistant over here, which, by the way, you can get to show up by going to the palettes menu right here and going to writing assistant. If you want to write that down to get this thing here, palettes writing assistant. And this does help you do certain things. For example, make subscripts. So I press this button right here. Do you see where I'm pointing at here, right there? That is a subscript button. You can make a subscript. I'm going to type an F because that's the function name, and I'm going to tab down to the subscript. And what I'm going to do is I'm going to type a V0 underscore, comma, Y0 underscore, tab over, and square bracket T underscore. I have emphasized this before. When you're defining functions for the first time, it's important to let Mathematica be alerted to what you are going to possibly change in your function. T does represent time. It's certainly a variable. It's certainly something that I'm changing. But I also want to let my initial velocity change and my initial height change if I want to. Why are these subscripts instead of in here? Because it's better to emphasize for your own benefit, not Mathematica's benefit, but for your own benefit, that T is the main independent variable, time. And these other things, well, I can change them if I want. I could change the initial velocity. I could change the initial height. Now I'm going to type a formula. I'm going to type colon equals. This formula is a formula that works in the Earth's gravitational field near the surface of the Earth for the height of an object under the influence of gravity when you ignore air resistance. It does start out the same as our other function, negative 4.9 t squared. Turns out the 4.9 comes from taking g, which is 9.8, and dividing by 2. Oops, that's supposed to be a square. Then add the initial velocity, which I'm calling v0, times t. Then add the initial height, y0. What I really have now is a family of functions. One function of t for each choice of initial velocity and initial height. And if I took v0 to be 0 and y0 to be 100, then it would be the exam problem. It'd be the function from the exam. But by allowing v0 and y0 to change, that's going to give me more power to see what happens if I do change the initial velocity and initial height. How, for example, does the time when it hits the ground change? Well, how does that change? This allows me to figure that out. And also make animated graphs to understand what's happening more deeply as well. Now that I've typed it like this, I can enter it. I entered it, I typed Shift, Enter. If I want to confirm that I've entered it, I can hit the subscript button again and type F tab V0, Y0, tab over T with no underscores, enter that and see the formula spit back in me. That means it is now stored in Mathematica's memory. That's good, that's what I want. And now what I can do is I can plot this function. I'm going to copy and paste. Remember, that's one of the benefits of Mathematica is you can take your other code and copy and paste it. That's what I'm doing here, copying and pasting it. And let me go ahead and replace the negative 4.9 t squared plus 100 with this function name. If I enter this as it is, it won't plot anything because it doesn't know what v0 and y0 are. See, I just entered it, nothing. But if I enter those numbers there, if I replace v0 with 0 and y0 with 100, I get the exact same plot as before. If I change v0 and y0, maybe I change v0 to be positive 50 instead of 0. It's going to update the graph. Of course, I probably want to make the plot range different. Yeah, because now you don't even see the plot. Let's let t go up to 10. Let's let y go up to 200. Now we see the plot. I better let t go past 10, say to 15. The graph changed. The 50 is the initial velocity. It's no longer 0, it's positive 50. Guess what? That's the slope of this graph at t equals 0. The velocity is the slope of the graph. And the velocity at t equals 0 is the slope of the graph, the slope of the tangent line right there at t equals 0. That slope is 50. That rate of change is 50. Can we confirm that? Yeah. Here's a quick way to do it. Let me copy and paste this function name down here. Let me put a prime in here standing for derivative, and let me replace t with 0. 50. That is the derivative. That's the velocity at time 0, the instantaneous velocity. Mathematica computed the derivative for me, and then I had it plug in 0. And if I now interpret that as a rate of change, that will allow me to approximate the height at, say, time 0.1. Think about it with me here. What is the height for this example at time 0? It's 100. The graph has a y-intercept of 100. The slope is 50. The rate of change is 50 there. So if I let time increase from 0 to 0.1, the change in y should be approximately 50 times 0.1, right? The 50 is the velocity. 50 times 0.1 is 5. When I enter this, it should be close to 55, or excuse me, 105. It's going to be a little bit lower, 104.951. Why? Because the graph is concave down. It's underneath this tangent line over here. Same conceptual point I was making on paper. Maybe I should write down what I just did. Same conceptual point. What I just did on Mathematica was I was trying to approximate for this new function. The new function is negative 4.9 t squared plus, what was my initial velocity, 50? I think it was 50, yeah. 50t plus 100. That's the new function for this new example. I just found, well, I know that f of 0 is 100. The initial height is still 100. And I just found that f prime of 0 is 50. So f of 0.1, well, it's f of 0 plus the change in y. And that's approximately f of 0 plus the derivative rate of change evaluated at t equals 0 times delta t. And this derivative can also be denoted by f prime of 0. Those are equivalent notations. F prime of 0 is easier to write. dy dt evaluated at t equals 0 is easier to interpret as a rate of change, as a velocity. By the way, this is nothing more than rate times time here. Remember in that lecture one that I had you watch first week of class? Over the weekend, I think. I emphasized that a lot of calculus is just generalizations of the equation, distance equals rate times time. That's what we're doing right now. This is an approximate distance or an approximate change in position. Distance equals rate times time. That formula only works exactly right when your rate, your speed, your velocity is constant. It's not really constant here, it's changing. But over small time intervals, if delta t is small, like 0.1, it will be approximately constant. So this should be a good approximation. And what do we get? F of 0 is 100. F prime of 0 is 50. Delta t is 0.1. So this is 100 plus 5, or 105 meters. That was our approximation using the derivative. In reality, using the function itself, you get 104.951, a little less than 105. Again, because the actual graph's concave down, whereas when we use the derivative, we're using a tangent line, a straight line to approximate the graph. This is easiest to think about with applications when you're thinking about these physics problems. But in reality, these ideas apply to thousands and thousands of examples, thousands and thousands, if not millions of applications. It just seems to be easiest, initially at least, to think of it in terms of motion. I think that's the easiest thing to think about. Yeah, if I retype f of 0 plus f prime of 0 times delta t, which is 0.1, I will get my 105. This is a linear approximation to the true answer. Let me show you more of the benefit of allowing these subscripts in here to allow me to change the initial velocity and change the initial height. Let me copy and paste this code down here. Let me now go ahead and change this back to a V0 and a Y0. Remember, if I enter this as is, nothing will happen because Mathematica doesn't know what V0 and Y0 are. However, I can embed this in another command, another function called manipulate, which is my favorite Mathematica function. Notice that this plot now is inside the manipulate. I'm nesting these commands here. I need a comma after the plot, and I need more input. This little red arrow here means Mathematica wants more input. Well, what kind of input? If I want to make an animation that allows me to change V0 and Y0, something like this will do. V0, comma 0, comma 50 inside curly braces, and say Y0, comma maybe 100, comma 150. What's this going to do? This is now going to produce a graph that I can change as V0 and Y0 change. If I enter this, here's what it looks like. And you see sliders for V0 and Y0. I can change the initial velocity and see how the graph of the height function versus time changes. I could also change the initial height and see how the graph changes. Or I could change both. And I can very quickly essentially solve infinitely many problems at once. Did you know that? You can do that in math. You can solve infinitely many problems all at once. For any given initial velocity between 0 and 50 at least, I can, and any initial height between 100 and 150, I can estimate the time when it's going to hit the ground. So for example, V0 is 19.15 and Y0 is 150. I see it's going to hit the ground close to time equals 8. If I change V0 to be 36.9, it looks like the time when it's going to hit the ground has gone up to about 10.5. I can solve infinitely many problems at once. There's much, much more I can do as well. Actually, that solving of infinitely many problems at once can be done algebraically as well. And this is something you should be able to do too. So let's think about the general case here. Y is a function of t is negative 4.9 t squared plus V0t plus Y0. This is something I emphasize a lot in the lectures. If you do decide to watch the lectures, I emphasize families of functions like this a lot, over and over again. And I emphasize it for good reason. These are really the most important kinds of things you can really get out of this class as a conceptual thing to think about applying in many areas is families of functions and what happens as parameters change. The V0 and Y0 are often called parameters. T is the independent variable, that's time. Y is the dependent variable, that's height. The initial velocity, initial height are often called parameters. They are constants for any given situation, but it's very interesting and informative to think about what happens as those constants change. And I can, for example, solve infinitely many problems at once. Figure out, for example, for an arbitrary initial velocity and an arbitrary initial height, when will it hit the ground? I can set this equal to 0 and solve for t Not by trying to factor this, because it would be too difficult to factor in the general case, but by using the quadratic formula. Where's that noise coming from? Is it outside, really? Wow. Very loud for being outside. Use the quadratic formula. The quadratic formula is an amazing piece of technology, and I call it technology for a good reason. It's very powerful. You can use it to solve a lot of problems, including this problem. Negative b means, in this case, negative v0 plus or minus the square root of the b squared minus 4 times a times c all over 2a. You remember that formula? Something you should remember, perhaps even for the rest of your life. Wow, that is loud. What are they doing? It's like he's breaking up the concrete or something. Okay, sorry about that. Yeah. Since we're after a positive root, and since this is negative, we can just take the plus. We don't have to do plus or minus. Plus square root, b squared will be b0 squared, minus 4 times a times c means minus 4 times this times this. Minus 4 times negative 4.9 times y0 all over 2a means all over 2 times negative 4.9. And actually, this is showing me I better take the minus sign here, actually. In general, it's plus or minus. Because of the negative down there, I'm actually going to want to take the minus one so that the negative signs cancel. So that was a spot where I was a little bit too cavalier in thinking I wanted the plus one right away. I actually want to take the minus one, and then the minus signs will cancel. The 2 minus signs there, you can factor out a negative 1 out of the top and then cancel it with the negative sign there to ultimately give you v0 over 9.8 plus, all the minus signs canceled, 1 over 9.8 times the square root of v0 squared. And if you simplify this, you'll get plus, what will it be here? 19.6 y0. That's the time when it's going to hit the ground. You can call it T hit. I've solved infinitely many problems at once. Functions like this. This is a function of 2 quantities, really. It's really, you might even call it a multivariable calculus function. It's telling you when it's going to hit the ground for an arbitrary initial velocity and an arbitrary initial height. You could give this a function a name. What should I call it? Maybe g of v0 comma y0. I could think of it as a function of the initial velocity and initial height. Wild, but true. Question? Sorry about that. We are getting close to the end here. If you want to, I will post this on YouTube and you can watch the end. Thankfully, we're close to the end. Is your computer working? Oh, okay, okay. All right, I just noticed and I was wondering if you were just listening and not being able to see it. Okay. That's a function. I could think of it as a function if I like. Oh, wait a minute, are v0 and y0 variables? Didn't I call them parameters? Well, yeah, they're parameters when I think of it this way, but you can always change your perspective on things. Here I was thinking of v0 and y0 as constants. Here, if I change my perspective, I could think of them as variables. This is a formula that's going to give me the time it hits the ground for an arbitrary initial velocity and arbitrary initial height. Although, this is only going to be valid if this thing under the square root is greater than or equal to 0, because if it were negative, we'd be getting an imaginary number there, which wouldn't make any real sense. So y0, Yeah, you wouldn't want y0 to be negative if v0 was 0, for example. Is it worthwhile thinking of it as a function? Is that a worthwhile thing? Could I plot it? Is the plot informative? Let me go ahead and type it into Mathematica. I'll call it G. G of, maybe I should go V0 underscore comma Y0 underscore. I'm not putting them as subscripts this time. That's okay. The formula is V0 over 9.8 plus, I'll write it as one fraction here, the square root of V0 squared plus 19.6 times Y0 over 9.8. Yeah, I can use this function to predict when I hit the ground. I can type in V0 is 0, Y0 is 100, and get our original solution to when it hits the ground. What was it? 4.52 seconds. Let's see if that works. 4.52 seconds. But I could type in some other initial velocity, like positive 50, and initial height, like 100, and figure out the time when it hits the ground. 11.92 seconds. I could even graph this. Plot G of V0, Y0. But wait a minute, if I plot it, what's the variable? Is it V0 or is it Y0? Well, it can be either one. Let's make it be V0 and let's set Y0 equal to 100. And let V0 change from, say, 0 to 100. I can plot the time when it hits the ground as a function of the initial velocity. And get this. It's not a straight line, it's almost straight. As the initial velocity goes up, the time when it hits the ground also goes up. And in fact, the graph is concave up. That must have some important real life consequences. Maybe we could interpret. And we could use calculus on this. We could figure out its derivative at any point to estimate not a velocity in this case, but the rate of change. In this case, it would be a rate of change of the time when it hits the ground, dt sub hit, with respect to changes in the initial velocity. You could figure that out. I'm not going to right now because it's past our ability to at the moment, but that could be figured out. So I'm making these in conceptual points at a level that is past what you would need to do for your homework for Friday. You're not going to have to do things this complicated on the homework for Friday. But I'm trying to make the main conceptual points. One big conceptual point being graphs and variables. Calculus is giving you ways of computing slopes of tangent lines to graphs at any points that you want. And that can help you estimate functions, like estimate the change in height, or the height at a short time later, like 0.1. But the most powerful application of this stuff is to considering situations that are a bit more general and really solve infinitely many problems at once. Solve for when you hit the ground based on an arbitrary initial velocity and initial height, for example. And I could make graphs there, and I could calculate derivatives there as well and find rates of change and estimate how this function is behaving. So within this kind of difficult stuff, I'm trying to emphasize the main conceptual points you should get out of stuff. One other conceptual point that I haven't had time for today that you should get out of doing the reading is that once you calculate derivatives at points, you come back and you realize, hey, I could have calculated that derivative at any point. Section 2.2 is titled the derivative at a point. Rate of change of the function at a, emphasis on the word at. F prime of a is this limit. Same kind of limit we've been doing. For our example today, a was 1 for the first example and 0 for the second example. And we use delta t instead of h, but it's the same idea. That's the derivative at some point a, but I also want you to read into the next section and be able to do some basic problems in the next section. Section 2.3 is titled the derivative function. The derivative function, because what you can do is you can do this limit at an arbitrary point x. X is arbitrary here. And different x's give you different answers. So what that means is the derivative really depends on x. It's a function of x. And being a function of x, it means you can graph it. So I haven't had time to do examples like you find in section 2.3, but if you studied this section well, you should study it well, you should be able to do some basic problems from section 2.3, and I will assign some for what's due on Friday. If you want more examples, I can try to find some parts of the lectures with more examples. You can also look on Khan Academy for not just the derivative at a point, but the derivative function that you can also graph. You can also use these formulas that are in the boxes here. This says if f of x is a constant function, its derivative is always 0. Constant functions have graphs that are horizontal lines. The slope is always 0 is what that means. This one says if f is a linear function, mx plus b, then the derivative is always the slope because the slope is constant. And this one, if you've taken calculus before, is probably the one thing you remember the most. The derivative of x to the n is n times x to the n minus 1. You take this power, this n, and bring it in front like this, and subtract 1 from the exponent. So in section 2.3, when you do those problems, if it doesn't say do it with a limit, you can use these formulas in these boxes in section 2.3. But in section 2.2, you should do limits. And in section 2.3, you should do limits if it says do a limit. If it says use the definition of derivative, that means use the limit definition. Okay? But these big conceptual points are important as well. And I will continue to re-emphasize them. All right, see you on Friday.